Hello, this is my English speaking practice, and I'm solving problems on LeetCode, and I'm I'm working on dynamic programming right now, but I have not solved the problem quickly, so I want to solve the dynamic programming problem quickly and elegantly. So this is my attempt. This is my fifth or sixth attempt. Let's go. Best time to buy and sell stock with cooldown. You are given an array prices where prices I is the price of a given stock on the ith day. Find the maximum profit you can achieve. You may complete as many transactions as you like, i.e. buy one and sell one share of the stock multiple times with the following restrictions. After you sell your stock, you cannot buy stock on the next day. Cool down one day. Note, you may not engage in multiple transactions simultaneously. You must sell the stock before you buy again. Yeah, makes sense. Yeah, I have solved these kinds of problems before. So I want to solve this. Quickly. So the time limit is 30 minutes. Yeah, 40 until 49. Okay. Best time to buy and sell stock with cooldown. Okay. Since we can do many transactions, as much as possible, as you like. Yeah, as we like. So yeah, this is I'm not sure this is kind of local optimal choices or not. I see. So in this case, if when we bought the share of stock on the first day, and after that, as you can see, there is 2 and 3. So normally, we want to sell the stock the third days, but if we do it, we have to take cool down after the day, so we cannot buy the stock at the price zero. Yeah, it's not good. So we have to sell the stock day 2, and yeah, after cooling down we can buy the stock with price 0, and we sell the stock with price 2, and the maximum profits be 3, right? Yeah. Okay, so we cannot we cannot solve the sub problem locally, because there are a lot of sub problems, and they are dependent. So yeah, the dynamic programming works here. Yeah, but we need to define the proper sub problem, how to how the sub problem can be solved, and how the transition works. But basically the DPN or DPI is like the maximum profit until the ice day. Yeah, and I think they also have a state, right? It's with stack or without stack, and also need a cool down or don't need. So there are 3 states we should manage, right? So the transition is like if it needs to cool down, we cannot do anything. Yeah, we cannot do anything. And if it doesn't need a cool down, we can buy a share of stock. If we have stock already, we can sell the stock, and to make a profit. Okay, that's a transition. So Yeah, we initialize the three array for each state. Okay, and let's initialize a base case, because this is like a bottom up solutions, so we need base case. And the price, the first day, on the very first day, we buy. Yeah, after the first day, we can buy the stock. We bought the stock with the price of day one. That is yeah, we have to pay the price day one. Okay, and this is, yeah, we don't have to do these two states for these two states. And sell no, when the we can buy, we can sell, we cannot do anything. We can buy, when we can buy, yeah, it's the state transit to cancel. So yeah, we can sell the share of stock at the end of the day I, and at the time the profits is can buy, yeah, but of course we can buy, we have an option not to buy this time, of course. So there are two patterns. So we choose the max profit when so still have a share of stock, or we buy the share of stock. So DP can buy -1 and pay for stock, right? And we can sell, and of course we have an option not to sell this time. Buy it, sell it this time. That is DP can I'm confused. Can sell means have share of stock, or yeah, buy a new share of stock. And DP can buy means we don't have stock at this state, so don't have. So at this point we can buy means we don't have share of stock and still don't have share of stock, or can buy means it might be transitioned from the cooling down. This is also, yeah, we do nothing. We do nothing anyway, and cannot do. So at the end of the day we might transition to we cannot do state. It's because we sell the stock. Yeah. Yeah. It's because we sell the stock. So DP can sell the stock I-1. That's a profit at the I-1 day, and make profit by selling a share of stock at with the price ith price. That's it. And yeah, return max. We don't care the state at the final day. We might have stock. Yeah, maybe it's not happen. Yeah, if you have share of stock at the final day, we shouldn't, yeah, we shouldn't buy stock. You shouldn't buy stock before. Okay, so maybe the max value might be can buy or cannot do, because we had better stock, we had better sell stock. Yeah, this is the runtime error. Oh, not I, n-1. That's the final day. Correct. When the price, I think is 1,000, 5,000. Oh, great. Nice, nicely done. Let me see the another solutions. So yeah, it's almost the same. Yeah, there are 3 states. So yeah. But it's okay. Yeah, great. Nice. But to be honest, I've solved similar I have solved similar problem before, like this. Yes, so I'm not satisfied. Let me try new question. Super ugly number. A super ugly number is a positive integer whose prime factors are in the array primes. Given an integer n and an array of integers primes, return the nth super ugly numbers. The nth super ugly number is guaranteed to fit in a 32-bit signed integer. What? Okay, let me. Super ugly number. Okay, let me clarify the problem. Given n and primes, and we have to return the nth super ugly number, and super ugly number is a positive integer whose prime factors are in the array primes. So maybe we have to generate the super primes, super ugly numbers like this, and yeah, return the nth number of it. Okay, and yeah, so the problem is, how do I generate these arrays? Yeah, it should be determined by the primes. Prime factors. There are prime factors. So 2 2 2 1 2 2 2s 1 7 3 2s 1 13 and 1 2 and 1 7 and 4 2s and 1 19 and 2 13s, 2 2s and 2 2s and 1 7 and 5 2s. Okay, so yeah, we have to generate this sequence. Okay, yeah, it's I also have solved similar problem to this problem, so I think I can. But basic strategy is generating these. This is also kinds of bottom-up solutions, because we can make it like this. Yeah. And the super ugly number must start with 1, and the prime length is 100 at most. Okay, got it. Okay, and there is a pattern to increase the to find the next number in this array. Yeah, so we can use primes. So yeah, prime indices here, and that points no indice prime times. Yeah, this means how many we use the prime. So EDX is prime indices. It's good. So, for example, we prepare the answer array. Not answer. We return nth. We should return nth number, but we have to prepare the array for storing the super ugly numbers. So yeah, that is this, and prime indices points the element. Okay, and for each element it can be increased by multiplication of primes. Okay, so for example, we have 1 as a base case, and the primes 2, 7, 13, 19. We have 2 and 7 and 13, 19. Yeah, as a default candidates, right? And yeah, between them the minimum number is 2, so we can append 2, and after that, since the 2 is appended to the super ugly numbers, we have also new candidates for regarding for 2s, because 7, 13, and 19 it's not used. It's still not used. So they are candidates. They are candidates, but the 2 is appended. So for 2 we have new candidates. So we can 2 times 2. We have we get 4 as a new candidate. So 4, 7, 13, 19. That's a candidate at this point. So, and the 4 is the smallest number, so we can append 4 to the array. Okay, and likewise we use 2. So for 2, the new candidate gonna be 4 times 2, that's 8. Okay, so the candidates would be 8, 9, 13, 19, and between them the smallest number is 7, so we choose 7. Okay, and for 7 we update. So yeah, okay, so how about this? For 7 we have we get 14. Yeah. Oh wait, we consume 7. Yeah, I understand. Okay, so For 7, the next value is 2, so we get 14. Okay, and 8, 14, 13, 19. Yeah, we choose 8 as a minimum number, so for 2 we can we can choose 7 as a multiplier, so we get 14, 14, 14, 13, 19. That's the candidates. And since the 13 is the minimum number, so we choose 13, and we can increment the index of 13 for 13. So we get, we move pointer, it points 2, so we get 26 as a new candidate. So 14, 14, 26, 19, and the 14 is a minimum number, so we choose 14, and in this case 14 is twice in the candidate array, so we update both of them. For two index points at 7, so we update the points to 8, so we get 16. And for 7, the index point at 2, so the point move to 4, so the new candidate's gonna be 28. 4 times 7, so we have new candidates like 16, 28, 26, and 19, and the minimum number is 16, so we append the 16. Okay, this is perfect. So this is the array for storing indices for each primes. Okay, and this is the super ugly numbers array. And yes. So okay, we initialize the super ugly number with n plus 1. Okay, and the base case is the head of the array is 1, and we initialize the indices with 0. Okay, and right now we are going to update the super ugly number. So primes. So we have to we have candidates. Candidates is the primes. This arrays. We can use this array as a candidates array. Okay, so the primes so the next num is the minimum value between the primes. Okay, and we append the nums next num. Okay, After that, we need to loop over primes, because we want to know which number is used. Okay, so prime in primes, and if p equals to next number, that means p is used here. P is used. Okay, so we also have an index, so p in enumerate primes, we get index, and prime indices at j, we increment and primes p primes we have to update primes j. It's okay, maybe we have to separate the candidate and primes. So here we want to copy the prime array as the candidates, and it's because in order, and the candidates is like this, candidates is used here, it's literally candidates, and for enumerating it's also candidates, and the prime indices at j is updated like this, and we also have to update candidates at the j, and it is prime indices is prime indices. So it's not a p, it's not a c, because it's candidate, and the prime indices. Okay, this points at the place of this array, super ugly numbers, and we can multiply it with the prime. So the p is like primes indices at j, okay, and p times no, primes is j, okay, and p, we can find the prime, and super ugly number, this index point the super ugly numbers, and we update candidates. Okay, that's it. And return nums the last index of the last element of the super ugly number, cause oh wait, n minus 1. Minus 1. Yeah. Oh, really? Oh, really? We cannot. Why? Ah, I see. Not append. We have to specify the index I. Correct. Oh, 1 and n. Yeah, we don't need to. Plus 1. That's correct. Okay, got it. Yeah, this is great. Yeah, the key thing is to manage the index, because yeah, this is bottom up solution, so we have to look at the numbers that already appeared. Yeah, because each number can be increased times some primes. Okay, so yeah, if we have 1, 2, 4, the 4 is made by 2 times 2. Yeah, so okay, so that's not important. For there is a 4, so we have 4 times 2, 4 times 7, 4 times 13, 4 times 19 as a candidates, but we don't need to calculate it every time, because yeah, there are still smaller candidates. Because, for example, for 7, yeah, we have a 7 at first. Because, yeah, it can be made up by 1 times 7. We have a 7 as a candidate. So when we get 4 in the super ugly number array, yeah, we just we have to update some candidates. In this case, 4 is 4 is 4 is the candidate of this, yeah. So we have to update this, only this. Mm. 14 is a good example. When we get 13 as a super ugly number, the candidate array would be like 14, 14, and 13 and 19. Okay, and we find the minimum number 14, and so we append the 14 into the super ugly number array, and after that we have to update the candidates, and there are 2 14 in the candidates. So for this yeah, for this the index points at 7, so the next candidate would be 2 times 8, that's 16. For 7, the index must be 2, so the next candidates would be 28. Okay, that's that is how it works. So we can have the minimum candidates for each primes. Okay, that's it. Yeah, but this problem is very similar to problems I solved today. It's a super ugly number, but yeah, this is it. Yeah, so I'm not satisfied with this, so let's go to the next problem. I want to solve the problem that I see for the first time perfectly. The thief has found himself a new place for his thievery again. There is only one entrance to this area called root. Besides the root, each house has one and only one parent house. After a tour, the smart thief realized that all houses in this place form a binary tree. It will automatically connect to the police if two directly linked houses were broken into on the same night. Given the root of the binary tree, return the maximum amount of money. Three, two, three, three, two. I see. So in this case, yeah. So we have to pick the node, pick the nodes, and that can be adjacent. So yeah, like this. Yes. And we have to maximize the number. That sums to we sum up that sums to okay. I see this problem for the first time, so this is the important. I want to solve this smartly. Okay. Only one parent. Each house has one and only one parent house. But it might have multiple children. Okay. Yeah. The first question to me. Do we have to generate all possible combinations? This case, all possible combination means the node IDs to pick. So 1, 2, 3. This case, if you pick one, if you pick the root node, we cannot pick this, but for this we have only one option, that is don't pick. But for this we have two options. We can pick or we don't pick. Either is fine. So there are a lot of combinations. So that's not optimal, I think. We have a better solution. It is we focus on the subproblems. Subproblems. Okay. And the subproblem is independent or dependent. It seems dependent because the subproblem is like what is the maximum profit, maximum amount of money visiting these trees. Okay. But it depends on the state of this. Yeah. If we visit this node, we cannot visit this node. So yeah, it automatically determined. So it's not independent problem, it's dependent. The subproblems are dependent each other. So we use dynamic programming, I think. But this is tree, so I think we have to the bottom-up solution would be difficult because we don't use index to point the node. This is like a linked list, so we use recursive. Yeah, and the recursive function, this function should return the maximum amount of money the thief can rob. Okay, and yeah, it takes node and it's optional tree node. Yeah, right. And if node is none, we cannot rob money at all. It returns 0. Rob this house. There is 2 branch. Skip this house. Okay. We have to take the flag for whether we can rob the house. If it's able, we rob this house. So we can yeah, we can get money. We can get money. We can get money. Is able. So we rob the money from this house. Money plus node value, right? And result is 0. Yeah. And for next house, we cannot rob the money, rob the house. So yeah, give false as a flag, and money is we don't have to give money because the money returns. Node write false. Okay. Yeah. Maybe result result 1. Result for branch 2. Yeah. For branch 1 and for branch 2, and B is true, on the right, and true. Okay, and return the maximum one, AB. Able is true. And for this kind of problem, the recursive function revisit the same node many times, so I think yeah, the cache works. This is possible? I don't know. This is a tree node. must be hashable to use the value as a key of the dict. But I don't know, so let me run it. Oh, it works. But wrong answer. Wrong answer. 3. Okay. I don't know. Skip this house. I see. It should be node is able. Node is able. Because the result is different if the flag is different. Okay. Okay. That makes sense. Not bad. Let me see the result. Great. It seems slow, but just 10 millisec, so I don't care about it. Yeah. Let me see the to left. So the left side is the value when rob the house, and the right side is yeah, that makes sense. So it's almost same. Okay, I think I'm good. This is good. And I somehow I feel like this is not difficult, so I'm not satisfied. I'm still not satisfied. So let me move on to the next. I want to solve difficult problem. Given an integer n, break it into the sum of k positive integers where k is greater than 2, and maximize the product of those integers. Given an integer n, break it into the sum of k positive numbers. Where k is greater than 2, greater than or equal to 2, and maximize the product of those integers. Okay. That's interesting. Okay. Something mathematical, integer break, and we are given an integer n. Okay. Okay. Oh, this is interesting. Okay. The first question to me: Do we have to generate all possible combinations? So here, all possible combination means the k positive integers, combinations of k positive integers. It's like, as an example, if n is 5, the one instance would be 1 1 1 1 1, like that. But the answer is we shouldn't do that because it's not efficient. So we think about the sub problems. Okay, so let's think about the sub problems. Maximize the product of those integers. I have no idea about this, so 3 3 4, it's 5 3 2 2 3 5 is 30. Yeah, 1 2 2 2 2 2 2 2 32. If we can find the if we can choose the locally optimal optimal option, we can solve this problem greedily. But I'm not sure. In this case, I'm not sure. But we can find subs problem like 10 minus 2. But I'm not sure choosing 2 is the best option, so maybe I have to check about this case. And also 4 is included in this case, so 5 Yeah, and regarding 7, that is maybe we don't need to do it for 7 because it's like this 7 times following my intuition I'm not sure. Intuition, yeah.
Intuition.
Following my intuition, we don't need to do that. But I don't know. What is the upper bound? 58. Okay, so we okay, but I cannot prove. I cannot prove that we don't have to do this case, so I will go for checking all possibilities. Not all possibilities, not all combinations. All combinations within one step. Okay, so in this case, n is 10. We can choose the four factors. Yeah, we can choose the 4 factors within 10. And yeah, this is like top-down problems. I feel like I can solve this problem top-down patterns. Let me think about the bottom-up solutions. Bottom-up solutions is, for example, if n is 1, the answer is 1. N is 2 is also, answer is 1. And if n is 3, it can be 2, 1, 1, 2. Yeah, the answer is 2. If n is 4, yeah, it should be 1, 3, and 2, 2. And we already calculated 1 for 1 2 and 3. Oh, that is good. Okay, so let me do it with bottom-up solutions. Top-down solutions be like this, but bottom-up is we prepare the DP array for storing the maximum value. Maximum product, maximum result of the product. So we initialize this array with zeros, and it's n plus 1 and dp0, dp1. We don't care about 0. We dp1 means but n start with 2 because we have to divide it, so it start with 2 and the dp2 is 1 because it's divided into 1 and 1, so the product is 1. And dp3 is 2 obviously, and dp4 is we are going to start with 4 n plus 1 return dpn dp4 for j in range 1 and oh wait, there are it's okay 1 and I. We have to how to find the primes. We have to generate primes until 58 until n range. Wait, primes. primes 2 times n plus 1. We are going to generate primes early and until n plus 1. Okay, and primes for I and Boolean value and enumerate primes b, we get primes as an index. Primes we and we check primes. What I was going to do here. DPI, we use DPI. maximum result of products 1 3, and regarding 4 1 3 so we can update the max dp dpi or p times dpi minus p. The answer is vouch. Okay, let me see. Can we create primes correctly? 0 1 2 3 5 7. Okay. The primes is good. But primes is 0 1 2. Start with 2. and we want to see the factors. Yeah, print. Determine I. Hmm? I have to. Okay, so for 4, the maximum product is 3. This is correct. For 5, the maximum result is, yeah, must be 6. Oh. Oh, I see, I see. Sometimes we shouldn't divide the number. The number itself might be greater than the number that made by the product. So I minus p may be greater than the dpi minus p, right? How about this? So this is not correct. So for 5, 6 is the big. Is the biggest. For 6, 9 is the biggest number. For 7, 12 is, yeah, 12 is the biggest number. For 8, huh? Four, 6. Oh, great. But wait. 4, 8. What is 18? What? How? 9 times 2. Okay. So with 2 and the 6 becomes 9. So the answer is 90. Okay. Seems good. Great. This is the bottom-up solution. What is it? What is it? What is it? So apparently we should use 3 as a factor as much as possible. And finally, it might be, n might be 2 or 1 or 2 or 4, 1 or 2 or 3, so multiple n. But I cannot prove this mathematically, so my solution is good. Okay. I'm satisfied with this, but I feel like I want to solve one more problem. Let me see. But I might quit. I might quit this problem on the way. Okay, given an integer n, return the counter of all numbers with unique digits x, where Okay, so count numbers with unique digits. For example, if the n is 2, we are thinking about the range from 0 to 100, and in the range there is nine numbers that have duplicate digits. Yeah, they don't meet the condition unique digits, so the answer is 91. And n is 8 at the most. That means the range would be million, 100 million at the most. So we shouldn't look at the every number, right? Okay, so the first question to me, do we have to generate all possible numbers or possible combinations? The answer is no, because it's not efficient, so it would be time limit exceeded. So we can solve this problem faster than the linear algorithm, I think. And we have to think about the sub problems because if n is 3, we have to think about 1 to 999 inclusive 1 to 999, but for 1 to 999 means one to 99 100 to like this, 900 to 999. 0. How about this one? $100. There is 10 plus 9. That is 112233. So and 1. This is 111. So the answer is 18. Is 82. Okay. So this is, yeah, this should be solved by bottom-up approach. Bottom-up approach would be fine here. First of all, if n is 0, the range is 0, so the output is 0. The output is 1. N is 1. Yeah, they are all unique, so the number is 10. Yep. And how do I solve n when the n is greater than 2? How about 9999 should be at 0. This is already calculated in the previous TP3. 1000 to 1,999. TP3 and we have another one. Okay, so TP3 we have to have to hmm? One. Let me see. For this, this is the example, and for this we have another one. So in this case, yeah, for that is 10 plus 10 and minus 1, that is 1. Okay, additionally 2, 2, 3, 3, 4, 4, 5, 5. Is this correct? $27. Hmm. 9, 27. Yeah, there must be pattern. So the answer is 27 times 9 plus 9. Yeah. Mm-hmm. 9 plus, because we can add 1 for each. So that is dp2 each, and 11x, but 111 is already included, so 9. This comes from 1x1 or 11x, and also 9. This comes from 1x1. Okay. So 9 times 9, 9. This is DP3. Right? Right. Yeah. For DP4 comes DP3 because we add yeah, we can add 1. We can add 1, and how about 11xx, 1x, 1 xx, 1x, 1xx1. Yeah. Maybe 81. Yes, so if how to we can calculate the base case. It's a unique number. Yeah, we want the number of duplicates. So in this case, 0. Yeah. For I in range 3 and dpi plus dp2, correct? Yeah. And we have to calculate this. This would come from like this. It's for dp3 like this. For dp4 is there are 5 digits, so we can choose we can choose 1 out of 5. Like this. We can choose 1 out of 4. 1, 2, 3, 4. Right. When I is 4, we have 4 patterns, and So we times 4 and it's 9 power of I minus 1. Yep. Oh wait, this is the number of duplicates, so the answer is let's go. Wow. Ah. 3 8 mm. Why? Oh, dpi minus 1 means 9. Stress 9. Huh. Why? N plus 1. Wow. Really? Really? Is this this means this case we append the 1 to the left side. 1 1 1 1 2 2 1 3 3 1 4 4 1 5 5, and for this 1 1 0 1 1 1, no, this x doesn't contain 1, so 1 1 0 1 1 2 like that. And this is also 101, 1, 2, 1, like that. We can count the duplicates. So dp3 oh, yeah, that's my but wrong. Count too much. It count too much. It count too much. Is this wrong? Really? Why this is not good? One, 2, 3, 4, 5, 6, 7, 8, 9. Yes. Times 9. 113, 114, 115, 116, 117, 118, 119. Right. 101, 121, 131, 141, 161, 171, 181, 191. That's all. So 27. All numbers with unique digits. Yeah, no duplicates. I think so. What? What is it? TP 9 times 9 times dp what is it? This case dp 2 nines, dp plus 2 nines, dp plus 3 this is like this, and for n minus 2 is correct, and when the I is 3, yeah, n power of 1, 9 power of 1, it's 9, and there is I is 3, so 3 minus 1. When n is 4, there are 3. Oh, close. But I'm not sure. dp plus 2 times 9. Twenty-seven times 9. Let me ask. Several mistakes in your counting logic. Let me break down the issue and show you correct approach. What is wrong? But I want to You're trying to count numbers with duplicate digits. Let me analyze where your logic breaks down. Well, you are trying to count numbers with duplicate digits for each length, subtract from total. Yeah, where your counting goes wrong. Yeah, for N3, looking at your comment, mistake 1, double counting. DP2 already includes numbers like 1111. Ah? One, two, three, four, five, six, seven, eight, nine. Hmm? 000. 4. But wait, there's still an issue. You are missing the pattern 1xx. Two x are the same but different from 1. Let me trace your calculation. dp2 is 9. Okay, for dp3 is 9. Yeah, cause this comes from where? There is still a double counting issue in your 3-digit calculation when you do 9 times dpi minus 1 plus temp for 3-digit numbers. The part counts one, two, two. Since you are getting a larger answer than expected, there is no obvious double counting in your pattern breakdown. The issue might be elsewhere. Missing the 00 pattern? Okay. Your formula calculation. Let me check the. You are missing, so you can't be. Oh, okay, I just missed. Okay. Zero pattern. 00. 100. Plus 1 is okay. I'm not sure. Okay, my solution is totally wrong. Yeah. I understand my solution works for only 3. So, yeah. Available digits. Cannot understand. Okay. So, we can choose we can choose 9. For I in range 2n plus 1, current count available digits. Yeah, So this here we think about two digit. So the first digit is already selected. So yeah, it would be 9 patterns. So we can start with 9, and then we choose the second digit, and we can choose 0 to 9. So there are 10 options, but we have to accept the number chosen at the first digits. So the number of available options is 9. So we so we are updating the answer. The total unique number is would be 81. It's 9 times 9. Okay, but the total because total is 10 already, because when we think about the only one digit, there are 10 unique numbers already we have. And we can we think about the 2-digit numbers, and the total number of unique is 81, but it would be added to the total like this. Okay, yes, and available digits okay. Because we have 10 unique numbers in a digit, okay, 0 to 9. And for this loop, when we decide the second digit, we use the number. We already use the 2 numbers, so the available options would be 8. Number of available options would be 8. Okay, so every time we calculate, we choose the number at the digit, the available options would decrease. Okay, so we return total. I see. The way I think was too complicated and might make the problem too difficult. That's not good. But today I'm 1, 2, 3, 4, 5, 6, 7, 8. I want to solve two more problem. two more problems. I want to solve two more problems. But it's time to break. So finish this stream.